Welcome to the Enabling Top-Level RTL Flows for the AMD Versal Adaptive SoC Tech Module. Here is the agenda for this Tech Module. We will focus on what is needed for the top-level RTL flows, the challenges with the NoC flow, understanding the new modular NoC flow, the challenges with the GT flow, understanding the new GT Wizard subsystem flow, understanding the new AXI switch IP core. Today, customers designing with the Versal Adaptive SoC have to use the Vivado IP integrator to configure key components like the SIPs, NoC, and gigabit transceivers. However, most users are still more comfortable with RTL development. These users face challenges with the IPI-based flow as it doesn't offer the same level of control and flexibility as RTL coding. To address these challenges, AMD is introducing an RTL-centric flow in Vivado 2024.2. This flow will allow users to configure their IPs using RTL wrappers, enabling more control and flexibility. This approach helps users to design more efficiently on the Versal platform. The module will cover two RTL-centric flows, one for the NoC, known as the modular NoC flow, and another for GTs with a new GT Wizard. Templates will be provided to help integrate RTL wrappers into block designs, allowing users to continue using the traditional RTL-centric approach. Before jumping to how we are enabling an RTL-centric flow for Versal Adaptive SoC designs, let's go over some of the challenges with the existing NoC flow. The Versal Programmable Network on Chip, or NoC, is an AXI interconnecting network for sharing data among multiple endpoints in Versal Adaptive SoCs. One of the major constraints when using the NoC in a design is that users have to go with the Vivado IP integrator flow, as the NoC can only be configured using the NoC IP available from the IP catalog. Also, the entire NoC from a design must be contained in a single BD, allowing only a single level of hierarchy. If designers have pre-existing AXI interfaces, then those interfaces must be rewritten in RTL so that they can route to the central BD, which increases complexity and the potential for errors. Additionally, with the existing NoC solution, it is difficult for multiple teams to access and modify the same BD due to challenges with file merging and revision control. For the dynamic function exchange use case, users need to be careful when dividing their design with a NoC into static and dynamic partitions. Designs with a NoC have to use the BDs for their reconfigurable modules. This requirement impacts the earlier assumption of putting the entire NoC in one BD, making the whole DFX process more complex. The first issue faced by users is related to AXI-based data crossing the DFX boundary. The process of integrating numerous signals crossing the DFX boundary can be quite complex and can lead to QOR challenges in future RMs, since the AXI pin locations on the RM boundary are not allowed to change. If the reconfigurable partition is using AXI interfaces instead of the NoC, users need additional IPs, such as the AXI shutdown IP for a safe working environment and the DFX decoupler IP for logical isolation capabilities. This often complicates the design and increases the required resources. Additionally, by not leveraging the advantages of the NoC, the design misses out on potential performance and scalability improvements. When users use the NoC for crossing the DFX boundary, the top-level RM must be a block design container, and any user RTL for the RM must be added to the BDC via module referencing or the package IP flows. This disrupts traditional RTL design flows, making it harder to maintain consistency and efficiency. Migration will become difficult when upgrading. We will see how a modular NoC with the integration of RTL at the top level will enable easier accessibility and resolve these issues more efficiently. Starting with the Vivado 2024.2 version, AMD has upgraded the NoC design entry flow, introducing what's now called a modular NoC. This upgrade is designed to make it easier for RTL users to seamlessly integrate NoC capabilities directly into their RTL design environment. The solution is designed to enable easy instantiation of a NoC by directly adding an MU, NoC master unit, and an SU, NoC slave unit, endpoints via XPM, Xilinx parameterized macro instantiations into an RTL design at any level of the design hierarchy. Parameterizing NoC characteristics by using RTL, which enables scalability, flexibility, and reuse. Reducing IP integrator usage to its minimum essentials without losing any NoC capabilities in an RTL design environment, allowing users to still use the IP integrator for accessing hardened endpoints like the DDRMC, SIPs, or HBM blocks. Defining NoC connections per module and reusing a module in different system-level projects. Keeping everything consistent without affecting the debug and simulation experience compared to the current IP integrator-based NoC solution. Third-party synthesis tools to compile the NoC via Xilinx parameterized macros, XPM instantiations. So, with all these solutions with the modular NoC and new design entry flow, the utilization of the NoC supporting dynamic function exchange will be easier to use, allowing for traditional top-level RTL flows with reconfigurable modules. Finally, there will be minimum impact on existing BDs, simulation, debug, and XSA generation flows. The modular NoC design entry flow consists of a three-step process. In the first step, users need to establish connection points by specifying the NMUs and NSUs by using XPMs in the RTL. Block designs can also be used to instantiate additional NMU and NSU instances. Next, users should define the connectivity, QoS, and bandwidth for these endpoints by using Xilinx design constraints. And then, in the final step, all the NoC instances are compiled using the new validate NoC tickle command at the system level. These steps maintain compatibility with the existing solutions, allowing access to hardened endpoints like in DDR memory, the SIPs block, or high bandwidth memory that reside in the Vivado IP integrator. This approach ensures that all essential simulation and debugging features remain intact, requiring minimal adjustments for integration with the Vitis Unified IDE or system software. Additionally, this solution provides the flexibility to accommodate future tool enhancements. We will discuss this process in detail in the next few slides. Step 1 is specifying the endpoints, that is, the NMUs and NSUs, using Xilinx parameterized macros. XPMs are simple, lightweight, and inline customizable solutions for common HDL flow use cases. They can also be considered as simple parameterizable IP. They are available as templates under the Language Templates section in the Vivado IDE. Users can enter and exit the NoC using these XPMs. In the XPM snippet here, the configuration of the NMU via parameters is highlighted. This template enables users to configure parameters like the data width, address width, ID width, and other settings. The NSU parameters can be similarly configured using this template. After the NMUs and NSUs are configured, the next step is to set the connectivity, quality of service, bandwidth, and addressing via XDCs. Users can use XDC files to do the following. Create connectivity or connections between the different NoC endpoints. Define QoS properties like the bandwidth and bursts on the created connections. Lock down NoC endpoints to specific locations. Set the aperture for the XPM NSUs. Apertures are defined at the egress point of the NoC. The third step is to run the validate NOC command. The command does the following. Looks for various NOC instances present in the BD, DCP, EDIF, and RTL. Identifies NOC-related XDC constraints comprising of connectivity, apertures, and QoS, and passes all this information to the NOC compiler, which creates a system-level NOC solution. Additionally, this command runs DRCs at a system level. The result provides a complete NOC solution that can be observed in the NOC viewer, showcasing the route results. Users can run this command manually, or the command is run by the flow automatically at 3 different stages: synth design, link design, and place design. Here is how a top-level view of a solution looks when all the pieces are put together. RTL Top has wrapped all instances and connections. It has the BD wrapper, which is a system block diagram with instances of the SIPs and NOC with connections to DDR, and there is an RTL module with an RTL AXI endpoint master connected to an XPM that instantiates an NMU connection onto the NOC. The XDC constraints are used to define the connection between the NMU and the DDR controller. The quality of service constraints are also being applied here. Now that you have seen how a modular NOC works, let's look at some supported use cases with this flow. Since the RTL contains XPM instances of the NMUs and NSUs, and a BD will have the NOC IP with AXI interfaces, various connection topologies are possible from a design entry standpoint. The first supported use case is when the RTL with an NMU is accessing NOC memory that resides in the BD with NSUs or memory controller ports. Here, the NOC IP is created and configured as part of the system BD, and it has connectivity support to DDR and HBM. It also has pseudo-channel support for HBM and interleaving for DDR. The next use case is a PS master to an RTL peripheral. Here, the processor or SIPs that resides in the BD is connected to a NOC with NMUs. The NMUs can access the endpoint peripherals with NSU XPMs that are instantiated in the top-level RTL. The SIPs is connected to the NOC over the CCI interface. The NSU supports the AXI4 full and AXI4 stream interfaces. The third use case is an RTL master to PS peripherals. Here, the RTL master is requesting access to a PS peripheral within the system BD. The NOC and SIPs are instantiated in the BD, and the RTL master with the NMU can connect to a PS peripheral via the NOC with an NSU. The last use case is data moving from RTL NMUs to RTL NSUs. Here, the connection is established with endpoints that reside in the RTL only. The SIPs is required for system configuration. This is a targeted use case for the AXI4 stream interface. Now that we have walked through the steps of using a modular NOC and reviewed its supported use cases, let's see how it compares with using the IP integrator only. For both flows, the BD is required, but with the modular NOC flow, the BD can be instantiated with the minimum required IP, such as the SIPs and DDR memory controllers. In the current flow, NOC validation is only possible within the BD, but now with a modular NOC, users can validate the NOC at the system level. Similarly, for the top-down and bottom-up design approaches, the modular NOC flow becomes more flexible when using RTL. With RTL, users can instantiate multiple NOCs which are easily accessible within the design hierarchy. Revision control is much easier due to the flow being primarily an RTL solution and not having to manage changes to block designs for additional NOC usage. Let's now turn our attention to gigabit transceivers. AMD Versal Adaptive SoC GTY, GTYP, and GTM transceivers provide high performance and integration at 7 nanometers, including serial I/O bandwidth and logic capacity. The GT Wizard flow generates a wrapper to instantiate the GT primitives and helps users configure their GTs. GT primitives consist of a single GT quad, the GT Quad base IP. The current GT flow provides 2 modes of operation. The first is with a standard protocol IP, also known as the AMD IP. This IP is added from the Vivado IP catalog and is used in the system. An example design is generated which configures the parameters specific to the protocol IP, and then block automation is used to instantiate and connect the GT primitive. The second mode is with custom IP. With this, an additional bridge IP is needed to bridge between the user's custom IP and the GT quad base. Block automation is then used to instantiate and connect the GT primitive. An IP integrator-centric flow facilitates the connection of one or more IPs to one or more GT quads. The initial setup relies on block automation and parameter propagation, which, while helpful, can lead to complications if modifications are needed. Design rule checks are performed to ensure that the IPs sharing a single GT quad are compatible with each other. This flow can hinder flexibility and customization, making it difficult to adapt designs to specific requirements. We will discuss further challenges with the existing GT Wizard in the next slide. GT usage is primarily centered around the IP integrator. Making changes to GT connections can complicate parameter propagation and block automation, creating additional difficulties. In addition, achieving flexibility and customization becomes more challenging when working outside of RTL, which limits the ability to tailor designs to specific needs. With block automation, the process of opening and closing designs becomes slow, and making any change will be time-consuming and hinder design iteration. There is also limited flexibility regarding clocks and resets, which complicates GT customization without RTL. Since GT parameter settings propagate from the AMD IP or a bridge IP for user IP to the GT quad base, users lack fine control over the GTs. Transitioning to an RTL-centric approach can effectively address these challenges. This shift would provide direct granular control, reduce unnecessary overhead, enhance flexibility, and offer a faster, more efficient way to access the GTs in Versal Adaptive SoCs. Starting from the Vivado 2024.2 release, the new Versal Adaptive SoC Transceivers Wizard subsystem marks a significant shift in transceiver design. This new wizard can be found in the IP catalog for all Versal devices. It transforms the traditional approach by recentering the design process around RTL. It is the default design entry approach for integrating Versal transceivers into designs and has a simple and intuitive feature selection flow. The new wizard provides an RTL wrapper created around GT primitives and allows for basic customization. It refocuses on an RTL approach with the same flow whether using RTL or the IP integrator. The IP is authored in user-readable RTL. It simplifies revision control by incorporating a traditional flow that includes XCI top-level and RTL output files. For both AMD IP and custom or third-party IP, there is an identical process eliminating the need for bridge IPs. The system also facilitates efficient sharing of one or more quads across multiple IPs, and it leverages the GT quad base IP for uniform GT output settings between the old and new workflows. With the new flow, block automation will no longer be supported for GT Wizard designs. Users can now instantiate a robust RTL wrapper that seamlessly integrates with the parent AMD IP, ensuring clean and efficient sharing of a single GT quad or even spanning across multiple quads. This innovation is poised to streamline the design process. With the new GT Wizard IP, users can choose the transceiver type, the number of interfaces or the number of IPs that are being connected to, the number of quads, and the interface configuration of each interface. The interface configurations can be done three ways. Using the Import File option, which allows users to point to a local TCL file that has the transceiver settings. The wizard then auto-populates the transceiver settings from this file. Using the Import Settings from AMD IP option. Manually using the Load button, which loads custom-defined interfaces. Each of these interfaces are configured independently by selecting the settings such as Preset, GT Lanes, and GT Direction. DRCs are then run within the wizard to identify incompatibilities. The quad interface mapping settings provide customization options to assign the lanes of each quad to various interfaces defined in the wrapper configuration. The GUI layout expands based on the number of quads selected in the wrapper and maps the quads to each interface. The GUI options to configure each quad consist of number of targeted interfaces, direction, TX and RX master clock source, interface to lane mapping, a read-only GUI option available to guide users on mapping multiple interfaces to a single quad and to check if the information provided in the quad interface mapping is correct. Interface to quad mapping. The design rule checks evaluate if the selected interfaces can be packed in the selected quad based on the physical resources. If the checks fail, an error message is provided to guide users to provide the correct customization options. The structural options section includes the clocking buffers and locations for them in the IP core or example design. Based on the transceiver settings, the customization options here can be limited to only the example design. The clock buffers can be self-contained within the RTL wrapper, meaning they are integrated directly into the design. Alternatively, users can choose to have them present in the example design for reuse. The additional ports options are configured on a quad-by-quad basis and include options for clock and loopback selections. The optional ports section options are common for all the lanes of an interface. These are less often used non-standard ports which are always available and can be for options like corner correction or out-of-band signaling. Based on the interface configuration, the ports of the TX-RX interfaces are enabled. The ports which are invalid for the configuration are disabled for enablement. Users can enable the optional ports according to design requirements. This is what the final GT Wizard-enabled RTL output looks like. At the top is a GT Wizard XCI, that is, an IP file. XCI files are accessible in the standard IP catalog, making it easy to manage and reuse configurations across different projects. Under the hood, the configured components are put together by wrapping them around with RTL. This Wizard RTL wrapper contains the self-contained resets and clock buffers that are generated within the wizard. Control over resets reduces the need for each IP to author reset state machines, simplifying the overall design workflow and providing a straightforward and integrated solution. For additional flexibility on clocks, an example clock topology can be included in the example design. This allows users to adapt the clock setup to specific needs. Underneath the wrapper is the fully validated GT Quadbase primitive. The whole RTL integration part makes the IP easy to understand, read, and modify. The RTL wrapper generates the .mem file for configuration and ensures the compatibility of all the configurations used in the wizard. With RTL implementation, all subblocks of the IP can be opened and reviewed. This transparency simplifies the process of understanding and verifying the design. Having human-readable RTL simplifies revision control, making it easier to track changes, manage updates, and ensure consistency across design iterations. Let's now do a walkthrough of the new GTWizard flow with an example. The flow starts with users generating the parent IP using either the IP catalog or Tcl scripts and/or custom IP. Here, users automate the loading of the AMD IP into the project to choose the GT settings. They can also use custom or third-party IPs with a Tcl file to ensure the correct settings are applied. Additionally, example designs are provided with connections to the GTWizard, making it easier to set up and configure a project. After the parent IP is ready, they will then generate the GTWizard, which provides an RTL wrapper created around GT quad primitives and allows for basic customization of transceiver modes, lane and quad mapping, optional ports enablement, and instantiation of clock and reset helper blocks. Users can even start with presets or can make their changes manually if there are no presets. After the IPs are generated, users then connect the clocks, resets, and port maps within the RTL or IP integrator. The new wizard allows a maximum of 8 interface IPs to be connected with the GT quad and has a one-time GUI entry stage for multiple line rate options to enable seamless dynamic rate switching without reprogramming the GT registers. The connectivity process is similar to what users are familiar with, utilizing parameter propagation but without block automation. Once everything is configured and connected, users can run the tools and the GTWizard will output an XCI file with an HDL wrapper. As part of the run, it implements full design rule checks between the parent and GTWizard IPs, ensuring compliance and compatibility throughout the design process. This flow eliminates the need for the transceiver's bridge IP and legacy wizard IP. Here are some advantages of the new GTWizard subsystem over the existing wizard. There is no longer a dependency on block automation for configuring the BDs. The new wizard subsystem provides easy configuration of BD instances without the time-consuming block automation process. The parameters of the GTs are now easily accessible with RTL wrappers. Modifying connections can be easily performed with the new wizard subsystem. Customization is simplified, making it easier to work with RTL. All these enhancements make the new GTWizard subsystem more efficient and accessible for users. In continuation of the efforts to enable the RTL flows, AMD is pleased to introduce the AXI switch IP, a fully customizable RTL-based IP providing a robust interconnect solution that serves as a bridge connecting AXI memory-mapped master devices to slave devices. It is an essential tool for those seeking to streamline their design architecture. The AXI switch IP core shares much of the functionality of the AXI Smart Connect IP, but is distinct in its availability exclusively through the AMD Vivado IP catalog. This IP is easily configurable with area-optimized, performance-optimized, and balanced modes via the customization GUI or through Tcl console commands, unlike AXI Smart Connect, which is mainly configured in the IP integrator environment. Once the IP has been customized, the generated component wrapper is intended to be instantiated into an RTL design or can be packaged into the custom IP.